exam.
Yes, we haven't chosen.
Haven't chosen it yet. We're going to do that this week. Okay? So, and we'll try to get it done as quickly as possible. I'm really sorry. I know people are trying to get away and so forth. Let me just say that the least conflict time seems to be Thursday, which is the end of the week, finals week. Okay? So, but we'll see. I'd like to have it earlier. Okay? I'd like to have it earlier. Let's see. Quiz 1 results. People did very well. Statistically, every time I give quiz 1, the performance is about 71 to 72% of the total number of points. And this time was no exception, except I considered this a harder exam than I normally give for quiz 1. So I think the fact that, I mean, it's funny. Why is it that it always comes out exactly 71 to 72%? I don't know. But it did this time as well. And you know, the fact that it's a harder exam than I normally give indicates that people are doing very well this term. So I'm very pleased with that. Also, interestingly, there was no statistical difference between the students taking the class in Singapore and the students at MIT. Okay, so that's a good that's good because our goal is to be able to establish essentially a remote campus for MIT students, and our admission criteria has been very stiff for people getting into that program. So I was very pleased that that things have gone well. Today I would like to talk about binary search trees. So we talked about them on Friday in recitation, and today what I'd like to do is start out with some sort of easy and surprising things, and then go on to some not so surprising and difficult things. Okay? So we'll start out with a sorting algorithm. Okay? Binary search tree sort. So this is a sorting algorithm where I start with an empty tree. Okay, and then I go through all of the inputs in my array, and I insert each element of the array into the tree. And then I perform an in-order tree walk. To provide the, which gives me the elements of T in sorted order. Okay, so everybody understand what this algorithm is? Okay, you basically just insert them in the tree, walk the tree. So let's just do an example just to make sure everybody is indeed warmed up. So here's an array. And so the first element I put in is 3. Okay, then I put in a 1. I compare it with the 3. It's smaller, so I put it over here. Then I put in the 8. It's larger. Okay. Okay. Then a 2. Boom, boom. Then a 6. Then a 7. And then a 5. Okay? And now what I do is I walk the tree. And walking the tree recursively, I print it out between the two things. So I visit the left child. Left child again is nil, so then I print out 1. Then I visit the right child, print out 2. Back, print out 3. Right, left, left, print out 5. Print out 6. Print out 7. Back, print out 8. And then I'm done. Okay? So how long does the tree walk take? What's the tree walk time here? on an array of n elements? Yeah. Yeah, theta n. Okay? Because all I'm doing is a constant amount of work at each node. Okay? In checking its children and printing itself out. Okay? So how long does it take to build the tree? Okay. How long does it take to build the tree? Yeah. Log n? That would be less than the number of elements. So it's not log. Excuse me? Theta n worst case? No. N squared worst case. Okay, n squared worst case. What's the situation that would make it n squared? Yeah, if it were basically just a linked list. Suppose they were already in sorted order. Okay, then it would make a chain running this way. Okay? And then each insertion, you'd have to go all the way down to the end. And so you'd get an arithmetic series of it taking n. You'd have a tree of height n. Okay? Also, if it were reverse sorted, you'd then get one that was the other way. Where have we seen this before, where sorted and reverse sorted are the worst cases? Quicksort. Quicksort. Okay, remember quicksort, if it's sorted or reverse sorted, same thing. Well, what's interesting here, and this is the following observation, which we'll look at, is that binary search tree sort is basically equivalent to quicksort. It's the same algorithm, okay, in some sense. Okay? In fact, it does exactly the same comparisons. But in a different order. So let me illustrate that for you. And that's pretty, I mean, if you looked at that, you wouldn't say, oh, that's quicksort, right? Hi, everyone. That's a jolly. I'm glad it wasn't something that couldn't be broadcast in Singapore, you know. Okay. So let's take a look at why I say that binary search tree sort and quicksort are essentially the same sort. Okay? So in quicksort, what I have is I start out with my array, 3, 1, 8, 2, 6, 7, 5. And I pick a partitioning element. Okay? 3, first element, say. Okay? Now notice that that's the first element that I pick in, which becomes the root of the tree. And notice that in this algorithm, every element is compared with 3 in the binary search tree algorithm. Well, in quicksort, when I do a partition, I partition it into 2 parts by comparing every element with 3, okay, to see if it's less than or equal to or greater than. And I get 2 lists here, 1, 2, and 8, 6, 7, 5. Now, in some versions of partition, you get, it scrambles these orders a little bit, as we discovered on the homework problem, where we're looking at the actual thing. But the scrambling the order doesn't really matter. The analysis goes through, even if the partition algorithm, in fact, maintains the input order. Okay? All you do is it just corresponds to, yeah, you screwed things up a little bit, but none of the combinatorics change. Okay? So now we pick, in quicksort, we pick the first element here as a partitioning element. Okay? And then we partition it. It's got 0 on one side and 2 on the other. And then we recursively then do this one. Okay? And then we go back and we start on the right-hand side. We pick this as a partitioning element. Okay? And we partition. In this case, everything falls on the left. Then we pick this element, and it partitions into 5 and 7. And then we do this one and then this one. Okay, so the operations that we're doing the comparisons are exactly the same comparisons. There's different bookkeeping that we're doing. One, we're doing a partitioning algorithm. The other, we're adding links into a tree. But the number of comparisons is not just the number is identical, the comparisons themselves are identical. Okay, it's the same algorithm. We're just doing them in a different order. In the order for quicksort, we first of all compare everything with 3, and then we recurse. In the binary search tree sort, we compare the first element with we compare the second element with 3, 1. Okay, and then we compare 8, and then we compare 2, but now we also compare 2 with 1. So the order has been scrambled a little bit, but exactly everyone comes through and compares with 3. And likewise, everything that's smaller than 3 gets compared with 1. And everything larger than 3 gets compared with 8. Okay, just as in quicksort. Okay? So as a consequence, the expected time to build the binary search tree is asymptotically the same as quicksort. Okay. And what's that? If I assume all inputs are equally likely, all input orderings are equally likely. Okay, that's, what is that? N log n, theta n log n, okay? Order n log n, okay, is the expected time. Okay? And so therefore, this search algorithm runs in order n log n time overall. Okay. And once again, also the worst case is the same as quicksort. Okay, so the worst case is the same. The expected case is the same, assuming all inputs are equally likely. Okay, let's see. Well, one of the things that we're interested in a search tree, which this analysis, this analogy can give us, is what's the depth of a node in a binary search tree if we construct it. Well, if we randomly build the search tree. By randomly build, what we mean is we take the inputs in, assuming all inputs are equally likely, and insert them. That's different from a random search tree on a set of elements. If you have a random search tree on a set of elements, that says consider all the different search trees that you could end up with and consider each of those to be equally likely. Okay, that turns out to be different. That's an exercise that I encourage you to look at as to why those two notions are different. But here what we're saying is randomly building a search tree is taking a bunch of numbers, you know, in where all inputs equally likely and creating a search tree. So how deep is the average node in such a tree? Is that a scratch or a? That's a scratch. So how deep do you think an average node is in a binary search tree?
It's log n, but binary log n height. So
well, it's not binary log n height. In fact, we haven't shown that, right? We don't know what the height is. We only know the average depth, in some sense. We know that the time to build it was n log n. Okay. So, but your intuition is correct. Okay? Your intuition is completely correct. It's about log n, order log n. So let's just show that. in some so by the way, this is the easy part. Then we get into the hard part. Okay. So the depth of a node is, so how does the depth of a node compare? How can I relate that? We have something where we understand that the total time to build it is proportional to the number of comparisons. We have a good characterization of how many comparisons because we've done the analysis of quicksort. So if I have a particular node in the tree, how can I relate it somehow to comparisons? How deep is the node? What's the depth of the node, the distance from the root? Yeah. The number of comparisons you put it through when? Because 3 gets compared with everything, but it's at depth 0. Excuse me? New hands. New hands. I like new hands. I think I'm going to start using the flying fickle finger of fate. Yeah.
When it is inserted?
When it's inserted what?
The number of comparisons.
Exactly. It's the number of comparisons when it's inserted. That tells you what the depth is. Okay? So the depth is just the number of comparisons, okay, during insert. Okay? And we're assuming that all input permutations are equally likely. So in that case, the average node depth, well, if I add up all of the node depths, what should I get? What do I get if I add up all the node depths? What is that related to? Yeah. Yeah, the total number of comparisons. The only way we compare is we add 1 for every time we insert it. Okay? So therefore, the average node depth is just the summation over the different nodes in the tree of the number of comparisons per node. Okay? And then, to get the average node depth, we just divide by n. Okay? And so that's equal to 1 over n times order n log n. Okay? So this is our quicksort analysis. Okay? And that's equal to order log n. Okay? So this shows that the average node depth is order log n, which is basically intuitive. This is why binary search trees are generally good. They generally have very good properties of the depth. And so if we're searching for things at random in the search tree, then each search on average, if we search for a random item in the tree, each search on average will cost us log n if I pick a number at random to search for. Of course, I could, okay, it doesn't mean that if I'm searching for things in the tree, an adversary couldn't always give me one that's really deep. Okay, that could happen. Okay? So this doesn't show that. And also an unsuccessful search, okay, where it's not in the tree, once again, might be deeper than the average node depth. Okay? And so this prompts us, so we know what the average node depth is, but what we'd much more like to know in order to bound performance of algorithms that run on this tree is what the height of the tree is. Okay? So the height isn't the same. The expected height of the tree is not the same as the expected node depth. The reason we're interested in height is because that tells us if we know what the expected height is, then once we've built the tree, we have very good idea of, doesn't matter what order we search for anything. Okay, it's bounded by the height. Okay, so and then we don't have to assume anything about the searching, whether it's successful, unsuccessful, whether the things we're searching for are random or not, if we know something about the height. Knowing something about the average node depth isn't the same. In fact, let me illustrate that. Okay, so it turns out that indeed the average tree height, if you use this random method of building a tree, okay, the average tree height the average binary search tree height is indeed order log n. But the argument about node depth doesn't show it. And in fact, this is a very hard argument, and we're going to do it. Okay, we're going to do it. Okay, it's a very hard argument. Okay, so let's see why these aren't the same. Okay, could somebody give me an idea of what kind of tree it would have to look like in order that the average node depth was order log n, but the height was asymptotically larger than log n? How could the height of the tree be asymptotically larger than log n, but the average node depth is log n? Somebody give me an idea of what a tree like that might look like? Is that a stretch or a... Yeah.
One particularly long branch and a bunch of shorter branches, so that averages out to be log n. But
good. Okay, so suppose you have a bunch of short branches, mostly short branches, and a more longer branch. Here's one particular example. Okay, so suppose that I have something that's essentially a complete binary tree. Okay, and so this height, as we're going to see, is going to be less than or equal to log n. Okay, but I happen to have a really long path here, and let me, for the purposes of this, say that the height of this tree is square root of n, okay, all the way down to there. So if I look along that one path, okay, I have a bunch of nodes going down this way. Okay. Now here's a tree that has height square root of n, okay, because the height is the depth of the deepest node, square root of n, because I just take this rightmost path here. Okay, let's compute its average node depth. Okay, so it's, let's see, well, there are at most n nodes, these guys here, that are at most log n deep. Okay, so so that's going to be n times log n plus, okay, the whole thing in the end is going to be over n, okay, because we have n nodes that we're dealing with, so we want the average node depth as opposed to the sum of the node depth. So the numerator is going to be the sum of the node depth. So we have n that are most log n, and then we have, so what's the average depth of stuff on this path, or what's the sum of the depths of things on this path? What's the sum of the depths? We're adding 1, okay, 0 plus 1 plus 2 plus 3 plus 4 plus 5 all the way down to square root of n. So what's that going to be equal to approximately? Yeah, it's basically square root of n times square root of n over 2. Right? Okay, so arithmetic series. Okay? And so that's just equal to, and that's just n over 2, of course, right? And so the total is here is order n log n over n, which is equal to order log n. Okay? So here it has pretty high height. In fact, we could actually make this height a bit larger. How much bigger could we make this height and still have average node depth being order log n? Yeah.
Is it the exponent instead of being 1/2 all the way up to 1, except the don't actually get to 1 pound? Is that correct?
That was too hard for me to understand.
Well, you have the square root of n, and the 1/2, whatever. Can it go up all the way up to 1?
Could it go all the way down to n?
Except it can't be.
Well, it couldn't go to n because then, right. So how deep could this be?
Right, all the way up to n, but not n.
Oh, all the way up to n, but not n. No, that would be too far. That would be too far, because what you would get here is something, if it were like n to the 3/4, for example, then you get n to the 3/4 squared over 2. Okay, the 2 doesn't matter, so n to the 3/4 squared, which would be n to the 1.5, by n, which would be then square root of n, you wouldn't get log n. So the key thing is how much bigger can I make this so it doesn't dominate that? Yeah.
Square root of n log n.
Square root of n log n, yeah. Okay, I can make this go all the way up to square root of n log n. And then I would have square root of n log n times square root of n log n over 2. And that would give me then n log n here, and so the total here is still n log n over n would be order log n. Okay, if it were bigger than square root of n log n asymptotically, then this term would dominate. Okay, and I would get something bigger than log n when I divided by n. Good. Okay, so we see that there is a difference between the height of the tree and its average depth. Okay, now we get into the hard stuff. Okay, because it turns out that this this is not an easy proof. And as with other proofs that I've given you that have been hard, you know, it's not like I expect you folks to be able to regurgitate this on an exam, okay, in detail. Okay, but by studying these hard arguments, the simpler arguments make more sense because there's a lot of instruction to be had in understanding a hard argument. Okay, so this is another hard argument, and well worth studying to understand the issues. So we're going to find out the height of a randomly built BST. Okay, and let me just say that I've seen at least 3 different proofs of this fact. Okay, and everyone is ingenious in some way. Okay, I have yet to see a proof of this fact that's trivial. Okay, everyone is ingenious because what you're trying to do is bound the expectation of the maximum of a set of things, and that's very tricky. Okay, because things are dependent. Max is a sort of a difficult function to deal with. Okay, so here's the outline for what we're going to do. Okay, there's 2 hard parts and then 1 easy part. Okay, so the first thing we're going to do, and actually I'm going to, you know, when I say some of these things, I'm actually simplifying things even beyond what's going on. But the first thing we're going to do is prove Jensen's inequality. Okay, which deals with convex functions. And what it says is that f of the expectation of a random variable is less than or equal to the expectation of f of the random variable. Okay? And this is true for any convex function f, excuse me. And random variable x. Okay? This property is always true if you have convexity, okay, of f. And the convex function that we're going to use for this is going to be essentially the exponential function. Okay, so we'll get into this in a moment. The second thing we're going to do is analyze an auxiliary notion, which is what we're going to call the exponential height. Exponential height of a randomly built BST on n nodes. And that's the function y sub n, which is equal 2 to the x sub n, where x sub n is the random variable for height. So this is the clever part of this argument, is that we don't actually analyze x to the n directly. We look at this auxiliary random variable, which is 2 to the height. And we'll see a little bit why we want to do that. This is the part where it gets on the border of where the intuition starts becoming a little more fleeting. Why is he taking 2 to this thing? Okay, and we'll talk a little bit about that at the end. And then the final step, which is the easy part, is once we have these in hand, we prove that 2 to the expectation of x to the n, which just is less than or equal to expectation of 2 to the x sub n. Okay, so 2 to the expectation of x to the n is less than e to the 2 to the x sub n. And what we're going to do is plug this in to show that. Okay. And then this thing is just equal to our expectation of y sub n. Okay. Which is what we're going to have calculated in here, is the expectation of y sub n. And we're going to show that that's in fact order n cubed. Okay. And so hence, if we take the logs of both sides here, okay, we get that the expectation of x sub n, the height itself, is equal to order log n. Okay, so it's rather involved argument. It's a difficult argument. Okay, but we're going to drag you through it. Okay, it'll be fun. Okay, be fun if you like math. Okay, if you don't like math, you shouldn't be in computer science. Okay. Good. Okay, so that's sort of the outline. So let's start out by reminding everybody what convexity is. So convexity is one of these notions that we see in so I got these boards confused at the beginning, is one of these notions that we see in calculus and then, you sort of forget about. Remember, I guess you see this in analytical geometry and in high school, right? They teach you convexity and so forth. So let's see if we remember whether my definition syncs up with what you folks remember. So a function f mapping reals to reals is convex if for all alpha and beta greater than 0, greater than or equal to 0, such that alpha plus beta equals 1, we have f of alpha x plus beta y is less than or equal to alpha f of x plus beta f of y for all x, y in the reals. Okay, so we'll see what this means in a second. Whoops, why did I say parens? I don't need parens there. I just want plus beta times f of y. Okay, so usually the way this is expressed, I expressed it this way because we're going to do a generalization of this definition. But usually it's expressed in terms of, say, an alpha and 1 minus alpha. So it says f of alpha x plus 1 minus alpha y, okay, and so forth. So that's the way you're probably used to seeing it. Let's just draw a picture to see what this means. I hope most of this is review. If not, you'll learn something. Okay? So here's, say, our x f of x axis, and what's the shape of the function if it's convex? Which way does it go? Okay, convexity. Yeah.
Twice differentiable convex function kind of goes upward.
Yeah, sort of goes upward, right? Sort of goes upward, holds water. Okay, so here's an f that sort of holds water. Okay. Okay. And so this theorem essentially says, well, this definition essentially says, well, here's a point x, and so this is f of x. And here's another point y. Okay, so this is f of y. Okay, and what this function is doing, as I let alpha range from 0 to 1, okay, is what does this thing do as alpha goes from 0 to 1? What does it sweep out? The line segment, good. Okay, line segment between f of x and f of y basically sweeps out that straight line. Did I make that straight? Well, not very. Okay. So this is, and so if I look at any alpha x plus beta y here, okay, what it's saying is that if I look at, so that's sweeping out a line segment, because this is a linear function, right? You can see this if you've had any linear algebra and so forth, okay? So what it's saying is that's sweeping out the line between, from this point x f of x and y f of y, okay? And what it's saying now, if it's convex, it's saying that if I look at these points here, well, here, this point here is just f of alpha x plus beta y. And this point here is the point alpha f of x plus beta f of y. Okay? And if it's convex, it's saying this thing is greater than or equal to that thing. Okay? That's all the definition is saying. And the key aspect is remembering that this is sort of the formulation by which we sweep out line segments. Okay? Okay, and so if we do that, then this is sort of our relationship. Okay? Everybody in sync with their recollection of convexity. Of course, then you go on in calculus to prove stronger properties of convexity for differentiable functions and so forth to determine whether things are convex and so forth. But this is the original definition they gave you before you learned things about, for example, the derivative method for determining convexity. Okay, any questions about convexity? Yeah?
So a straight line will also be convex.
So a straight line by this definition is convex, yes. Okay, by this definition. There are issues when you get to the boundary conditions of whether you want to consider this to be equal or less than or equal if this is, I mean, it's just a boundary condition. But generally, yeah, okay, it's a perfectly good way to phrase it. Okay, different people, different textbooks will vary as to what's important to them. For us, the boundary conditions, I'm happy, if you have a linear function, I'm happy to consider it as convex. Okay, this theorem will still be true that I want to prove, Jensen's inequality. Okay, it's just that you'll get equality here. Okay, rather than strict. And for our purposes, it doesn't matter if it's equal or less than or equal. We will get to things in the class, by the way, where we do care about less than or equal versus less than. But right now, for the sizes of things, we really don't care about whether it's less than or equal or less than. Okay? Everybody with me? Okay, that's the easy part. So here's a convexity lemma. This is a generalization of this fact. Okay. What I'm amazed, by the way, about things like this is, and people sometimes don't believe me, but all this mathematics really helps you engineer stuff better, if you understand this. It's really remarkable to me that I have extensive experience engineering, supercomputers and internet systems and, building languages, building, large programs and so forth. And I'm always amazed at how simplifying a theoretical approach to things can be. Okay? Stops you from flailing around a lot and building stuff that doesn't work. It's really amazing. Okay, so this is very good discipline for those of you who are not going to enjoy our sojourn through the math world today. Okay. Okay, so let F be convex. And let alpha 1, alpha 2, alpha n be non-negative constants whose sum is 1. Okay, so this is just a generalization of the setup up here. That's why I sort of wrote it with alpha and beta there. Okay? Then, for any set x1 up to xn, okay, of numbers, we have f of summation k equals 1 to n alpha k xk less than or equal to sum k equals 1 to n alpha k f of x sub k. So this is saying the same thing, okay, if k equals 2. K equals 2, it says f of the sum of these things, okay, is less than or equal to the sum of each of the alphas times f of the individual ones. Okay. Now, just thinking ahead a little bit, why do I care about something like this? How am I going to use that here? What are my alphas going to be in something like this? Yeah?
Possible values of your random variables?
No, it's not going to be possible values of my random, because the alphas are all less than or equal to 1. They're all between 0 and 1. So yeah, good. So probabilities. Okay? So it's going to be probabilities. That's where we're going to use this. Okay? And it's going to let us, therefore, get this kind of behavior. Okay? Okay, to prove this theorem here. Okay, let's prove this. Actually, what I'm going to use is a more general convexity lemma than what I'm showing here. So the one that I need to use in practice has to be for an infinite set of n's, of alpha n's. But we're going to just do it for the finite case because it gives you the intuition and so forth. And it's the infinite case. Actually, what you really want to do is you want to do this with the integrals, and then you handle it for everything. Okay, but we're just going to do it for some simple things because it takes us through some good math, and it'll give you the intuition for what we're doing. So let's prove this. How do you think we prove this? What's the one-word outline of the proof here? Induction. Good. Induction on n, in this case. Okay. In fact, this was something on the quiz. Happens every year. People say, I'm going to do induction. They don't tell me what they're inducting on. You should never say induction. You should always say induction on and give the variable that you're inducting on. Okay? Just an important hint for doing well is to make sure that you don't just sort of say induction and then you've got to pick the variable you're inducting on. You've got to be explicit about that. So let's start out for n equals 1. Okay, we could start out with 2 because it's just saying that, but we'll start with 1 just to show that we can. Okay, so for n equals 1, what's alpha 1 equal to? Easy questions. So somebody give me, somebody way in the back corner there. 1, good. Okay, alpha 1 is equal to 1 because the sum has got to be 1 and there's only one of them. So it better be 1, okay? Okay, and hence we have f of alpha 1 x1 is equal to alpha 1 f of x1, actually less than or equal to, trivially. Okay, because if alpha 1 is 1, it's just saying f of x1 is less than or equal to 1 times f of x1. Okay, pretty trivial. Okay, so now we do the inductive step. This actually, I was on the airplane doing this between Singapore and here, and I didn't have any books because, you know, carrying that book is not exactly what you want to do when you're off traveling. Okay, that's why I encourage everybody, if you're traveling with it between your dorm room and here, you know, I recommend, you know, if you have a place to put stuff here on campus, you should buy 2 copies of the book. Okay, and that way you don't have to carry it. And I say that with all sincerity. Okay. Okay, with no ulterior motives whatsoever. It's just okay. So let's start out. We have f of summation k equals 1 to n of alpha k xk. So this took me a little bit to figure out how you do this. Okay, it wasn't too hard, but it was one of these things where, you know, figuring out exactly what the trick is to make it short took a little bit of playing around. So what I'm going to do here is I'm going to split out, since I want something that inductively I can show, I'm going to split out the top term. So let's call that, let's say that's f of alpha n xn plus, and now the trick is that if I just said the sum of k equals 1 to n minus 1 of alpha k xk, the problem is I can't apply my inductive hypothesis. Okay, what's missing if I just said the sum of alpha k xk, k equals 1 to n minus 1? Why can't I apply the inductive hypothesis? New hands here. Why can't I just split it off, apply the inductive hypothesis, and be done? Yeah.
Cover the case where n equals 1.
Excuse me?
It doesn't cover the case where n equals 1.
No. So for this is for you know, we're assuming n is greater than 1 because I already handled the base case. Yeah. Yeah, the sum, if I take the sum of k equals 1 to n minus 1 of the alpha k, it's not equal to 1. Okay, it's going to be, what is it going to be equal to? 1 minus alpha n. Okay, so what can I do here to make it so that it's equal, so that the sum is equal to 1? Okay, so what you do is you scale all the alphas by 1 minus alpha n. So what you get is you get 1 minus alpha n times the sum of k equals 1 to n minus 1 of alpha k over 1 minus alpha n xk. Okay, and now the point is that this part now, the sum of these terms here is 1. Okay, of these new scaled alphas, these alpha primes, okay, is now 1. Okay, because the sum of the numerator here is 1 minus alpha n. And now I get to cancel. Okay, so now I can apply my convexity argument, okay, because I have here alpha n times something plus 1 minus alpha n times something else. Okay? And that's the structure in which I get to apply convexity. When I have f of that, that's less than or equal to alpha n f of xn plus 1 minus alpha n f of what remains. Sum k equals 1 to n minus 1, alpha k, 1 minus alpha n xk. Okay, so that's because of convexity. Okay, I just did convexity on two variables. Okay, the alpha n and the 1 minus alpha n. Okay. Now that thing, I say, is less than or equal to alpha n f of x sub n plus 1 minus alpha n times, and now I'm going to, this is an f of a with a set of alphas, these alpha primes here, if I look at the ratio here, which satisfy my inductive hypothesis. Okay? It's a fewer number of terms. Okay? Fewer terms here, only n minus 1 terms. Okay? So therefore, I can apply the theorem here and say that's less than or equal to k equals 1 to n of this. So I get 1 minus alpha n times the sum of k equals 1 to n minus 1 of alpha k over 1 minus alpha n. Okay, that's the alphas times f of x sub k. So that's the inductive hypothesis. Okay. Now that's equal to, what's that equal to? So now I get to cancel this thing back out that I had in there before. Okay? So this is really just the sum of k equals 1 to n of alpha k f of x to the k. This is alpha n x to the n. So I just get sum of k equals 1 to n of alpha k f of x sub k. Okay? And that's what I had to show. So a bit of algebra, a little bit of trick to how to make the convexity apply, because convexity is defined with two arguments and then the inductive hypothesis. Okay? And the trick is to make sure I've satisfied the property that the sum of these constants that I have here is equal to 1. Okay? Because that's what I needed in order to make this work. Okay, and this is also, it turns out, true if I take n to infinity, if I have an infinite number of these and so forth. Okay, so it's also, and in fact, that's the way we're going to use it, okay, in general. So let's prove Jensen's inequality. We're now ready to do that. Let's see. I think I can erase this outline. I think the outline, we're going to do it, so I don't think I'm losing anything by. So let's see how we apply convexity in proving Jensen's inequality. Okay, so let f be convex, and let x be a random variable. Okay? And he says, Jensen, I think it's a he, but I'm not sure, f of e of x is less than e of f of x. Okay? And the proof is actually pretty short. Okay, so we have f of e of x, okay, is equal to, well, we just take the definition of the expectation. So that's f of, and this is where actually the using integrals is actually a cleaner way to do this, because then it applies to everything. But let's just assume that we're dealing with integers here, okay, because it gives you the same intuition. So we'll take k equals minus infinity to infinity of k times the probability that x equals k. That's just the definition of expectation over all the values it can take. And we're just assuming here that that it's defined on a real domain. I mean on an integer domain. Okay, if I wanted to do it with reals, I'd do the same thing. It would just be integral. Okay, and okay, so the integrals are more general here. Okay. And now I apply the convexity lemma. And that says this is less than or equal to what? Somebody apply the convexity lemma for me? This corner's too noisy, too many hands. Too many hands over here. That corner back there, not so many hands. Teach me, teach me. No, teaching. Learning, learning, learning. Means you lean forward in your seats. Your hands up. How about back over there somewhere? I see half a dozen people there who don't regularly raise their hands. That's it. Look uncomfortable. Oh, I feel uncomfortable. Oh, okay, good.
Equal to the summation from negative to infinity, and then k times.
Well,
Oh, equal to the x.
what's that?
And you put the
F of k, good. Times probability x equals k. Good. Okay? That's just applying the convexity lemma. Okay? And that, ladies and gentlemen, is just the expectation of f of x. Now this last step, this is true. That's actually, if you think about it, trickier to understand than just simply saying it. Because technically, it really should be, this summation, in order to go to this step, should be something like f of k times probability that some x is equal to f of k. And the f should be over here. And so now this turns out to be true. And this is true all the time. You can rely on that. But you should think through it because there's some set theoretic understanding. Because basically it says that, if I coalesce a bunch of things that have equal values, I'm still having it equal to those values, still has the same probability mass. So this is a tricky argument, okay? But it's true, okay? It's one of the things you can rely upon in probability. I'm not sure if they cover this in 6042, this property here, that this is equal to the expectation of f of x. Okay, it seems sort of obvious, but In fact, if you look at the definition of expectation as defined in terms of a single random variable times the probability that that variable is equal to a value. Okay? And here I'm saying it's f of x times the probability that the argument, that the variable is equal to the argument. So, okay, so it's a little bit tricky there, but it's true. Okay? And it does take some, you want to think about that a little bit set theoretic. It'll help you, if you work on that, it'll help you understand it. So now we have Jensen's inequality. Now notice the convexity lemma I applied with an infinite number of terms. Okay, and I only proved it for a finite number. Okay, don't worry about it. It's still true. Okay, so there's a hole in my proof here. Okay, but I didn't want to get all the way down the hairy lane here. Okay, let's get to what we want to do, which is analyze the height. So this is all warm-up. Okay, Jensen's inequality. Did they do Jensen's inequality in 6042? No. Okay, I didn't think so. Not when I taught 6042 last. That was a few years ago. Okay, so let's analyze the height. And this is really a beautiful argument. Beautiful argument. It's the simplest argument I've seen for this fact. The other arguments I've seen use much more heavy-duty mathematics. And this uses sort of understandable mathematics. They do Chernoff bounds in 6042. So I see some nods and some shakes, so that's probably a bad sign. Okay. So, because there's another argument that uses Chernoff bounds. There's another one that uses generating functions. Okay, those are the three arguments I know. Okay. So this one I think is the simplest. This is the simplest. Okay, so let's just review here. Xn is the random variable denoting the height of our binary search tree with all perms of the inputs equally likely. Okay. And y sub n is our exponential height. That's just 2 to the x sub n. Okay. So let's take a look. So now we're back in BST world. Okay, out of convex world for the moment. Okay, and we're back into BST world. And we're looking at our binary search tree. And we're looking at the top node, because that's where we start, because everything we're going to do is going to be recursive. And that node has some rank in the ordered set. We're assuming all inputs are distinct and so forth. Okay, no two key values are the same. So let's say that the root has rank k. Okay, so the idea is here's the root of our tree, and that means that there are k minus 1 things that are going to fall over here, and how many things over here? N minus k. Good. Okay, so suppose that it has rank k. We're going to analyze what happens, and then we're going to use indicator random variables and so forth to handle all of the different values k could take on. Okay, so what does that say about x sub n? If I know that the root has rank k, then x sub n, how can I express x sub n in terms of smaller values of the variable x? So x is just the height. We're not getting into exponential height yet. So what's x sub n equal to? Yeah.
X sub k minus 1 and x sub n minus k.
Close. Plus 1. Good. Okay. So I've got 1 for this guy, for the height of this guy. Okay, plus it's going to be the height of these. Okay. So x sub n is 1 plus the max of x sub k minus 1, x sub n minus k. And the reason is because all permutations being equally likely means that both of these guys are randomly built binary search trees. Okay? Okay, and for the same reason that when we analyze quicksort, we can analyze each piece of the two things, because the permutations are all equally likely over here as they are over here. Okay, the fact that you compared them with this value doesn't change the number of different ways you can permute things over here versus the number you can do over there. Okay, so we get that. Okay, so let's now look at the exponential height here. So y sub n is equal to what? Can we get a recursive equation? This is only for intuition. Now we're getting into the exponential height, which is what the core of the argument is going to be. So this is just 2 to the x to the n. So I know what x to the n is. What's y sub n in terms of? How about over here? Right, this side is too many. I think it's because what? Because this, I see, because this classroom is sort of set off to this side. I've never sort of really, I teach to there, right? You folks are all in right field, okay? Because the middle of the classroom is here. It's not here. That's why these people are more responsive. I knew it had nothing to do with you folks. It's just you're sitting in the wrong place. Okay, so let me stand over here, okay, and see if I can get eye contact with this crowd here, okay? Okay, so what's y sub n? Somebody over here. Oh, okay, got to raise your hand. Oh, you can't raise your hand. You're too cold. Okay, that's fine. Yeah, 2 times 2 to the max of this, but suppose I want to express it in y. So 2 times is right. That's good. Don't need any logs. So you're right. So we're going to have essentially 2 to the max of this. Can I get the max down below? If I have the max, 2 to the max of a and b, that's just max of 2 to the a, 2 to the b. So therefore, this is just times max of yk minus 1, yn minus k. Good. Okay? Because of this fact. Okay? Because we know that, 2 to the max of something is max of 2 things. Okay. Okay. Now the part we've all been waiting for. Indicator random variables. Okay. We all love indicator random variables because they let us take case analyses and reduce them to summations. Yes. Okay. So z sub nk is going to be 1 if the root has rank k. And this is an easy one. Somebody on this side of the room, okay? Somebody on this side. Raise your hand. Raise your hand. Okay, the person 3 from the back on the end. 1, 2, 3. 0. All right. Okay, otherwise. Good. Okay. So you're following along. That's great. Okay. So this is how we're going to define. This is very similar to the way we defined it when we were analyzing quicksort. Okay. Very similar. Okay. So the probability that z sub n k is equal to 1 is, as we know, just the expectation of z sub n k, and that's equal to one over n. Good. Okay? And so, therefore, we can write y sub n now as a summation to handle all the cases, k equals 1 to n, of z sub n k times 2 times the max of y sub k minus 1, y sub n minus k. Okay. So we now have a recurrence, and of course what we want to do, very much like quicksort, is simplify the recurrence. So that we can actually solve it. Okay, in other words, let's get rid of the indicator random variables. Okay, and so let's take expectations of both sides. Okay, and that's equal, I claim, to summation k equals 1 to n, expectation of z n k times 2 times max of y k minus 1, y n minus k. Why is that? This should be old hat now, right? We've seen this one before. Yeah. Linearity of expectation. Good. Okay. That, I claim, is equal to why is that? Why is that? And make sure I teach the whole class here. Independence, that's right. What's independent here? Independence of Zn k with, basically independence of the root rank from all of the structure of all the subtrees and so forth. Okay, it doesn't matter what the root rank is. You've got the same problem to solve on either side. Okay? Okay, that's less than or equal to Okay, here I did something I don't want people to do. I did 2 steps at once. Whenever you do 2 steps at once, guaranteed, if you make a mistake, it's hard to find. Always do just 1 step at once. But here I did 2 steps at once. Okay. So what are the 2 steps? What are the 2 steps? Can you see? Yeah, that's one of them. E sub z n k is just 1 over n. So that came out over here. Good. Okay, so that's E of z n k equals 1 over n. That's one of them. What's the other one? That took care of that term. What must I be doing here? Yeah.
We have two non-negative things in the max, then the sum of the two is greater than that.
Right. So I'm using the sum is greater than or equal to the max. That's only true if they're non-negative. If it's negative, it's not true. One of these is negative. But if they're non-negative, then the smallest one can be is 0. So you can't be subtracting anything. So therefore, the sum is a bound. The sum is a bound on the max. Okay? So the max of two non-negative numbers is less than or equal to their sum. Okay? And finally, that's equal to, I should stack this, but I don't have room. I do this right, n minus 1, this should be. What's going on there? Yeah. Yeah, so we're running through every term twice. Okay, if I look at the whole range here from k equals 1 to n, I see y sub k minus 1 twice, once here and once here. Okay? So therefore, I get only twice the number, so that's where I get the 4 instead of the 2 over n. And then I re-indexed it going from k equals 0 to n minus 1 rather than k equals 1 to n of y sub k minus 1. I just re-indexed that. Okay? And so this now is really simple compared to what we started with. Okay? So each term appears twice to re-index. So let's solve this. And we're almost done here. Okay. So we're going to use substitution to show the expectation of y sub n is less than or equal to cn cubed for some constant c large enough to handle the initial conditions. So we just substitute in expectation of y sub n is less than or equal to, okay, so I just substitute in here 4 over n summation k equals 0 to n minus 1 of ck cubed. Okay, just straight substitution. Okay, that's less than or equal. I'm going to use the integral method here. So let me pull the c out, 4c over n. And this summation is just less than or equal to integral 0 to n. So remember when you use the integral method, you always take the limit and add 1, okay, of x cubed dx. Somebody who's in the integration B champion, do we have any integration B champions here? No? How about participants? Your champion? No. Okay. Okay, so what's the value of this? X to the 4th over 4. Good. So that's equal to 4c over n, n to the 4th over 4. Okay. That's good. Now I get cancellation. Ooh, good stuff. Because that's equal to cn cubed. Magic. 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 All right, we're really moving here. So let's just finish this off quick. Okay, so therefore 2 to the expectation of n is less than or equal to expectation of 2 to the x sub n. Where do I get that from? Jensen. Good. Our friend Jensen. I don't know who Jensen is. Okay, but He's got an inequality named after him. It's pretty good. Okay. And this is equal to what? That's just the expectation of yn. And that's less than or equal to what? So this is just the definition. This is Cn cubed. That's what we showed. Okay? So therefore, the expectation of x sub n is less than or equal to, I just take log of this. Okay? 3 log n. Okay? Because if I take the log of this, I get expectation of n plus O of 1. Magic. Okay. Now, why is this analysis so hard? This is hard analysis. Okay? This is hard analysis. I had to go through this exponential. Why not just do the same thing but with x sub n rather than y sub n? Yeah.
A very uneven tree. You need to get the expectation as opposed to.
Yeah. But why? So there's a real math trick going on here. This is not an easy question. Okay. Essentially, what's going on is that if I look at this is one of these things where I've got to teach this a few more times before I really get the intuition to explain better. This is the first time I've taught this particular argument. So if I look at max, one of the key things is I'm using max of A and B, okay, and I'm bounding that by A plus B, where A plus B are non-negative. Okay? And the problem with this is a very weak bound, okay, because, you know, as absolute value of A minus B gets big, okay, this approaches this very slowly. But if I look at the same thing with exponentials, okay, that's less than or equal to 2 to the A plus 2 to the B, then this bound here now, as A to B gets big, this bound goes to the max really quickly. Okay, it's a really tight bound. Okay, so as that gets bigger, the max, you know, the other thing is just falling away exponentially with the difference. And then this is an ugly thing normally to have to deal with. Sums of exponentials are not good. Products of exponentials easy to deal with. Sums of exponentials, bleh. Okay, and that's where Jensen comes in, using convexity of exponentials. Okay, so here's a little food for thought. Okay, think about it a little bit. One is actually look to see what happens when you try to do the analysis on x sub n directly. Go through this exact thing and sort of see where does it fall apart? Where do I need the more powerful mathematics? Another question is, why does it have to be exponential? Why can't I do this, say, with a quadratic or a cubic? Okay, will that work? Why or why not? Okay, take a look and see where that things. And the last thing is see if you can find a simpler argument. Because I found a simpler argument than the one in the book, if it's correct. Might be wrong, but if it's correct, it's simpler. Okay.